So, Samuel, pre-trained models, huh? You're saying they're like ready-made programs?
Yeah, exactly. Think of them as experts who've already done the heavy lifting.
So, they've learned from tons of data?
Tons and tons. Massive data sets. Like millions of images, or even more.
And what makes them so useful?
Well, they've been trained to do specific tasks. Like recognizing objects in pictures, or creating new ones. It saves a lot of time and effort, compared to training a model from scratch.
But how do these models learn?
Well, you give them a massive data set. Think about a kid learning to read. They see a bunch of words and eventually figure out what they mean.
So the input-output pairs are like a library of examples?
Precisely. The model learns patterns, relationships, and connections between the input images and the desired output.
Wait, so they can describe an image in English?
That's right. They've been trained to correlate images with sentences.
That's amazing. How does this help in practical application?
Imagine automatically tagging photos, or even generating realistic images for design.
That's wild. But what are the limitations?
Well, the model is only as good as the training data it saw. If the training data is biased or incomplete, the model might reflect those issues in its output.
So, if the training dataset had a lot of pictures of people of one race, the model might not be accurate about others?
Exactly. Bias is a serious concern. We need to be aware of that.
And this PyTorch Hub thing, what's that?
It's a tool for easily getting access to pre-trained models. It's like a library.
So, essentially, a one-stop shop for pre-trained models?
That's a good way of putting it. It makes it much easier for everyone to leverage these powerful tools.
Makes sense. And if I'm new to PyTorch, should I skip this chapter?
Well, it depends. If you're just looking for the basics of deep learning, then you might be better off going to another chapter. But if you want to learn how to use these powerful models, then this is a great place to start.
Makes sense. So, this PyTorch Hub is like a toolkit for pre-trained models?
Exactly. A quick way to get started.
Excellent. Thanks, Samuel. That was helpful. So, Samuel, we're diving into pre-trained networks. Can you give us the gist?
Sure. We're using a network already trained to recognize objects. Think of it like having a super smart assistant that's already seen millions of images.
Millions of images? That's a lot. How does it work, exactly?
It learns patterns from a huge dataset, like AlexNet. The images are labeled with what's in them, like dog or cat.
So, it's learned to associate images with labels. Cool. But how does it work on my pictures?
You feed your image to the network. It's pre-processed, a bit like cleaning up the image. Then it gives you a list of possible labels, like dog, cat, etc., ranked by how sure it is.
So, it guesses based on learned patterns. What if it guesses wrong?
It happens. Some pictures are tricky. The network's not perfect. It's a powerful tool, though, for quick image recognition.
AlexNet? That sounds massive. What's behind it?
It's a huge database, a major dataset. Academic competitions helped build it, like the AlexNet Large-Scale Visual Recognition Challenge.
Competitions drive innovation, I see. What kind of tasks are in these competitions?
Lots, like identifying objects, classifying scenes, and figuring out object positions. They keep changing.
So it's a moving target. That AlexNet dataset uses WordNet. Tell us about WordNet.
It's a huge English language database. Think dictionaries, thesauruses, but much, much deeper. It's part of the labeling system for AlexNet.
Gotcha. So, the network generates scores for each label. How are these scores useful?
The highest score points to the most likely label. It's a way of measuring how confident the network is.
How about the input images? What's the deal with the tensors?
Images are turned into numerical data, tensors. It's like representing colors and positions as numbers. The network understands that. It's essential.
So, to summarize, we feed images in, the network identifies likely objects. Is there anything else we should know?
We need to prep the data and understand the network structure. It's a step-by-step process. But it's powerful.
So, Samuel, we're diving into pre-trained networks. Tell us about these AlexNet trained models.
Yeah, these are networks that have already learned a ton about images. Imagine them as really smart image recognizers.
So, they've seen a massive dataset?
Exactly. ImageNet has millions of images. The networks learned what features make a cat different from a dog, or a car different from a truck, just by looking at all those examples.
Why use these pre-trained models?
Well, training a network from scratch takes ages and a lot of data. These pre-trained ones save tons of time and resources. You get a good starting point, almost like a head start.
So, Torch Vision is a good place to find them.
Exactly. It has popular architectures like AlexNet, ResNet, and Inception. They're different ways to arrange the thinking parts of the network.
Can you explain the difference between AlexNet and ResNet, say?
Sure. Think of AlexNet as a simpler, earlier approach. ResNet, well, it's more complex and much more effective. It has this clever way of making deeper networks work better.
Deeper? That's fascinating.
Yeah, the depth of the network refers to the layers. And more layers don't always mean better results.
So, how do we use one of these models?
We load one using code. There's a way to get those models from Torch Vision. You don't have to build them from scratch, which saves tons of time.
You mentioned these lowercase names in the code. What are they?
Lowercase names like AlexNet, ResNet 18, or ResNet 101 are functions. They give you a ready-to-use model.
Interesting. So, the naming is logical?
Very. ResNet 101 is a ResNet model with 101 layers. The more layers, theoretically, the better it can recognize patterns.
So if we want to use one, what do we do next?
Now we can use the model to classify images. We feed it images, and it will give us predictions.
So, AlexNet, right? This 2012 winner. How revolutionary was it really?
Well, it was a big deal. Imagine a huge leap in image recognition accuracy. It showed deep learning could actually work for this.
15.4% top 5 error rate? That sounds good.
Compared to the second best, which wasn't deep learning, it was a huge improvement. That huge difference is what really drove home the potential of deep learning for vision.
So, it's a small network now by modern standards?
Yeah, absolutely. Modern networks are far more complex. But it's great for a first look. We get to see how it works.
Right. Why use something simple?
It's a perfect stepping stone. You learn the underlying principles, then move on to more powerful architectures.
And the picture? That AlexNet diagram?
It's a visual representation of the layers. You see stacked filters, processing images. Each filter reduces the image size, step by step.
So, these filters are like functions?
Exactly. They transform the input. And the training process teaches them how to do this transformation. It learns which features to pick up.
And then we have this vector output, this 4096 element thing.
Yeah, that's the summary of all the processing. It gets put into a format to help figure out what's in the image, assigning probabilities to different classes.
Okay, but how do we use this AlexNet thing?
You create an object, an instance, like a AlexNet equals models.alexnet. Then you can feed data through it.
Okay, but what if the network's untrained?
Then it just spits out random results. It needs to be trained or have pre-trained weights loaded.
Pre-trained weights?
Those are the learned numbers for processing, which already know the rules for different classes. It's like giving it a head start. You load those learned values into the network. It's much faster than training it yourself, and more practical for many tasks.
Interesting. So, loading those weights is crucial.
Exactly. It's like starting with a well-tuned engine.
So the lowercase names for functions? There's shortcuts for creating the network with pre-trained weights, is that right?
Yeah, they make it easier, since the pre-trained networks have a specific structure. There's nothing stopping you from building from scratch, but it's a time saver to have preloaded models.
Makes sense. And we'll dive into exactly how the training works and why loading pre-trained weights is important later. Thanks, Samuel. So, Samuel, you mentioned ResNet 101. Can you break down why these super deep networks are important?
Yeah, absolutely. Before ResNets, training networks this deep was really tricky. Imagine trying to build a super tall tower. The further up you go, the the harder it is to keep it stable. Same with deep neural networks. The signal gets lost in the layers.
So, ResNet's fixed that?
Exactly. They introduce these shortcuts, or residual connections. They allow the signal to skip some layers, sort of like a shortcut in the tower. This helps the signal flow better, preventing that signal loss problem.
Wow, that's a clever trick. And that 101-layer network? That's a significant architecture.
Absolutely. That's a lot of layers, a lot of parameters to optimize. That's why it was trained on a massive dataset, ImageNet, which has millions of images. Having that data is key to training such a large and complex network. Imagine trying to train a super accurate machine to identify an object with so few examples, or training a car to drive in the worst weather conditions with only one data point. That just won't work, right?
So, we're downloading pre-trained weights. Why not train from scratch?
Training from scratch takes incredibly long. Pre-trained weights offer a good starting point. You've already learned a lot from the ImageNet dataset. It's like having a blueprint for a house. You can use that blueprint to get started, then adjust it to your specific needs. Think of it as using the experience of others. It gives you a head start.
And 44.5 million parameters? That's a lot. How does that affect its use in real-world applications?
Absolutely. That many parameters mean a potentially powerful network that can solve more complex tasks. Imagine all the calculations needed. But it also means more computing resources and potential for longer training times. It might not be suitable for all use cases, like mobile devices. You might need a lighter version.
Okay, so ResNets are a significant leap in neural network training. You're saying pre-trained models give us an advantage?
Exactly. It's like having a knowledgeable mentor in a field who helps you get started on a tough problem. It saves time and resources, especially for complex problems. You have this huge foundation from a very large dataset, and you can then adapt it for new tasks.
Okay, Samuel, so we got this ResNet 101 model. What exactly is it?
Well, Alfred, it's a deep learning model for image recognition, specifically designed for computer vision tasks.
And what's with this 101?
That's the number of repeating blocks, those bottleneck modules, inside. Think of it like layers upon layers of image processing filters.
So, more layers mean more processing?
Exactly. More layers mean more complexity, potentially more accuracy, but also more computational cost. 101 layers are a lot.
But what does this model actually do?
It takes an image as input, and it essentially tries to figure out what's in it. It works by identifying patterns in the pixels.
Like what kind of patterns?
It looks for everything from simple shapes to intricate details. It breaks down the image into many parts and identifies connections, eventually giving you a score for each possible category.
Like if I put a picture of a dog in, what comes out?
A list of probabilities. The highest probability would be the most likely class. For example, golden retriever or pug.
And this ResNet part?
ResNet stands for residual networks. It has a clever way of training deep networks. Essentially, it helps the network learn better from previous layers. It's quite efficient.
So it's pre-trained?
Yeah. This ResNet 101 is often pre-trained on a massive dataset like ImageNet. So, it already knows a lot about what different kinds of images look like.
How do we prepare our images for this model?
We need to pre-process them. The code shows transformations, like resizing and cropping. This makes the images the right size for input.
Why normalize them?
Normalizing ensures the image values are within the same range as the ones it was trained on. Otherwise, the model won't interpret them correctly. This is crucial.
So, we've got this pre-processing pipeline. What's the deal with that?
It's a series of steps, like resizing, cropping, and converting to a numerical format the model can handle. Essential for compatibility and making sure your data is ready for the network.
Makes sense. So, we load the picture.
Then we use these pre-processing steps. Critical for any deep learning image analysis, so the model can interpret input data accurately.
And then what? How do we get predictions?
We feed the pre-processed image, as a tensor, to the model. Then the model runs computations and gives you the scores.
Interesting. So, we're essentially translating our visual data into a format the model understands. So, we've got this trained model ready to do some image recognition. How do we actually get it to see a new picture?
Right. That process is called inference. We need to put the model in evaluation mode.
Evaluation mode? Why is that necessary?
Well, some parts of the model, like batch normalization or dropout, work differently during training and testing. Evaluation mode tells the model to behave predictably. It's like switching it to a testing setting.
Okay, I see. And how does this evaluation mode work in practice?
There's usually a simple line of code, like ResNet eval, that flips a switch in the model.
And after that, how do we use the model?
Then you feed it a new image, a batch of them. The model processes this input, giving you a bunch of scores. Each score represents how likely the image is to be a specific thing, like a dog, or a cat, or a table.
A bunch of scores. So, how do we interpret that?
We find the highest score. That tells us what the model thinks the image is. There's a tool in the code to find the maximum score.
So, we're looking for the biggest number in a list of numbers, and that number points to the class prediction?
Exactly. And we can also see the probabilities for the next few most likely predictions.
That's fascinating. Can you explain probabilities, Samuel?
These are the model's confidence levels. The top prediction gets the highest confidence level, then the next ones decrease.
Wow. So, let's say the model sees a picture and says golden retriever with 96% confidence. Does that mean it's always right?
No, not always. The model learns from examples. If the image has a similar appearance to dogs, the 96% confidence is high, but it's important to remember that a high confidence prediction doesn't guarantee correctness. The model might be misled.
So, what are the potential issues?
The model only sees what it has seen during training. If something is fundamentally different, the model may give the wrong answer, even with high confidence. For instance, a model trained on pictures of dogs and cats might confidently think a picture of a horse is a dog, just because it's a quadruped and has similar image features.
Interesting. So, the more data the model has, the better?
Usually, yes. But even with lots of data, some errors and bias.
So, what's our takeaway?
This model won a competition. It's very good at what it's trained on. But we need to be mindful of the limitations. We need to understand the model's training data to correctly interpret its output.
So, Samuel, you're saying this model like fakes it till it makes it? That's intriguing. Like, how does that work in the art world exactly?
Yeah, Alfred. Think about it. If you're trying to create a convincing forgery, you can't just wing it. You need feedback.
Right? You can't just randomly paint and hope it works.
Exactly. This model uses a process similar to how you learn a skill. Instead of random trial and error, you get feedback. It's like a student getting a critique from their professor.
So, you're saying a real art historian, that's the teacher?
Exactly. The art historian is the one who identifies the weaknesses in the forgery, and the model uses that info to learn and refine its output. This could lead to extremely sophisticated forgeries.
Wow. So, you're saying this method can learn to imitate any style?
Potentially. The key is data. The more data it's fed, the more it can learn the nuances of different artistic styles.
But isn't this just taking the work of an artist, copying it, and making it seem different? Isn't that a problem ethically?
Well, it's a complex question, Alfred. This process is similar to how we've trained models for various tasks. But, there's always that element of manipulation. You're effectively automating the process of learning. But that's what we're trying to achieve. It could be used for creating incredibly realistic images or for artistic interpretation. But ethical considerations are crucial. It will change what authenticity means.
This is deeply troubling, Samuel. What about the implications for things beyond art forgery, like for digital photography or video?
The implications are huge. Imagine convincingly faked images being used as evidence in a trial. What if video footage is faked with this technology? The concept of photographic evidence is fundamentally challenged.
So, this is more than just a creative challenge. It has huge legal and societal implications. What are the potential countermeasures to this, Samuel? How do we prevent the use of such a technique for malicious purposes?
That's a critical question. We're in the very early stages of understanding this technology's potential. Methods like watermarking and sophisticated analysis techniques are being explored to identify these forgeries. But they'll need to be constantly evolving, since this technology will likely adapt as well.
Okay, Samuel, so this GN game you're talking about, it sounds like a fascinating arms race between two AI systems.
Exactly. Imagine two rivals, a painter and a critic. The painter tries to create realistic fakes, while the critic tries to spot the fakes.
So, the painter's the generator, right?
Precisely. It's trying to make convincing images, starting from random noise. Think of it like an artist learning to paint, getting feedback from their tutor.
And the critic is the discriminator?
Yes, the discriminator judges the realism of the images. It tries to tell the difference between real and fake.
So, they both get better through this competition?
Absolutely. The generator gets better at creating realistic fakes, and the discriminator gets better at recognizing the fakes.
How does this feedback loop actually work?
The discriminator identifies flaws in the fakes. This information is fed back to the generator, telling it where to improve its artwork.
So, the generator learns from its mistakes?
That's right. It's not about one network winning, but improving the art of creation and detection in tandem.
And the goal is perfect forgery, right?
Not quite. The goal is to produce images indistinguishable from real ones. Think about a situation where you mix real and fake images. A human expert should be unable to tell which is which.
That's a high bar. What are some real-world applications of GANs?
Image generation is a big one. Creating realistic faces, or even making photorealistic pictures from simple sketches, is possible. You can even use them to improve existing images, by removing noise or increasing detail.
Interesting. So it's like a super-powered photo editor?
Exactly. And there are uses in medicine. GANs can create synthetic medical images, which can be helpful for training purposes. Imagine training radiologists on realistic images, without having access to sensitive patient data.
Okay, now let's imagine a problem like the generator starts creating images, but the discriminator is still too good. What happens?
The generator will remain stuck in a less developed state. The discriminator will still identify its flaws, and the generator would not learn properly from the feedback.
What if the discriminator is too bad?
Then the generator has an easy time passing its creations as authentic. The feedback mechanism is broken. Both networks need to be balanced and in constant competition.
So, cycle GANs, right? They're neat. How do these work exactly?
Yeah, they're a powerful advancement on GANs. Basically, they can translate images between different domains, like horse to zebra.
No need for match pairs?
Exactly. No need for a horse picture next to a zebra picture. Imagine you only have a bunch of horses, a bunch of zebras.
How do they manage to learn the translation?
It's clever. They have two generators. One turns horses into zebras, the other turns zebras back into horses. And two discriminators, one checking if the zebra looks real, the other checking the horse.
So, two generators, two checks. It's like a double-check system?
Precisely. The cycle part comes in. The zebra-to-horse generator takes the fake zebra, turns it back to a horse. The discriminator judges if this horse is real.
Why is that important?
This cycle forces the system to learn a consistent translation. If the zebra-to-horse conversion isn't accurate, the cycle fails. Think of it like a feedback loop.
Makes sense. But how does it learn the anatomy?
The system learns the relationships between parts. It doesn't know mane or leg. But it figures out how the positions and shapes of parts relate. So the final horse has a corresponding shape even though it never learned about a mane in a supervised manner.
Wow. So, no labels?
Correct. That's the genius of it. Just tons of pictures of horses and zebras.
What about potential issues? Are there any pitfalls?
Well, like with any GAN, training can be tricky. Getting the generators and discriminators to balance can be tough. Also, getting realistic results can take a lot of data and computation.
So, this is a huge leap in image translation. Any real-world applications?
Definitely. Think of medical images. Could translate one type of scan into another, or maybe even create synthetic data for training other models. Self-driving cars could even use this to adapt to different lighting conditions.
So, This cycle GAN, it's pretty cool. It turns horses into zebras. How does that magic work?
Well, it's a type of neural network. Think of it like a really sophisticated pattern recognizer.
A pattern recognizer? Like it sees the horse, and bam, it's a zebra?
Precisely. It's trained on a massive dataset. Lots of horse pictures, lots of zebra pictures. The network learns the subtle differences between the two.
So, it learns the features? Like the stripes, the mane?
Exactly. The network maps one to the other. It essentially learns the transformation. It's trained by comparing images, not by anyone explicitly telling it what a zebra stripe looks like.
Wow, that's powerful. So, there's no human guidance?
No direct supervision. It's learning the relationship between the two, based on the vast amount of data. The network learns to produce an image that would fool a discriminator into thinking it was a zebra.
What about the model itself, the ResNet generator? Can you describe it a bit?
It's an architecture, a design of the neural network. The details are intricate and specific. For now, the important part is that it's a generator, making new images from the existing ones.
So, it's not just copying. It's creating something new, drawing from the dataset's inherent information?
It's like a sculptor learning to carve a horse, then using that knowledge to create a zebra. But it's not perfect. The results, although not perfect, show how the network can understand and manipulate the data from an image.
Interesting. So, we load pre-trained weights? What does that even mean?
It's like giving the network a recipe, instructions learned during training to tell the network how to create the zebra. It already knows how to make those connections.
And then we feed it a horse image.
The network processes the image, analyzes the features. It then modifies the pixels in a way that transforms the horse image into a zebra image.
But what if there's a human riding the horse/zebra? Does that throw the network off?
The network may struggle a bit with details like the human, but it's quite impressive given the lack of explicit guidance.
So, you're saying the network generalizes those images? Not just remembering specific horse images.
Yes, exactly. It learns general features, like overall shape and color patterns, making it able to apply its knowledge creatively to new images.
So this image captioning model, it's basically like a translator for images, right?
Exactly. It takes an image and tells us what's in it, using words.
Cool. And how does it do that? Is it magic?
Not magic, more like clever math. It has two parts.
2 parts? Explain that.
First, a part that looks at the image and figures out what's there.
Like, identifies objects?
Yeah, like a cat, a table, a mouse. It converts the picture into numbers.
Okay, so numbers representing objects. Then what?
Then a second part, a recurrent network, takes those numbers and puts them together to create a sentence.
So, it's like describing the image step by step?
Kind of, but it builds a complete caption, a story. The recurrent part is key.
Recurrent? What makes it recurrent?
It remembers previous words to generate the next one. It's crucial for creating a meaningful grammatical sentence.
So, this is a model trained on images and captions?
Precisely. It learns from pairs of images and descriptions to understand how to link visual details to language.
That sounds powerful. Any downsides? Limitations?
Yeah, it's only as good as the training data. If the training data is biased, the model might reflect that bias in its captions.
So, like if the dataset mostly shows cats, it might always talk about cats?
Exactly. And accuracy can vary depending on the complexity of the image.
Interesting. So, these models can really analyze images, generate descriptions, and are helpful. But are there use cases for this beyond simple descriptions?
Definitely. Imagine generating captions for visually impaired people, or automatically tagging images for search engines, or even creating movie summaries for movie stills.
Wow, that's huge. So, Neural Talk 2. This model, it can describe images, right?
Yeah, it's pretty cool. It takes an image and tries to generate a caption.
Can you give us a basic idea of how it works?
It's using a deep learning model. Think of it as a really sophisticated pattern recognition machine. It learns from a massive dataset of images and their descriptions.
So, it's like looking at a million pictures of cats and dogs, and then learning how to describe them?
Exactly. The model finds patterns between the visuals and the text.
And it's impressive it can describe a horse on a beach, right?
Yeah, it's like learning to understand the world through images. And it can work with images that have never seen before, and still make pretty good descriptions.
But what about those zebra images? It got the animal right, but it had some issues.
That's a crucial point. It shows a weakness. The model is only as good as the data it was trained on. If the training data doesn't have a rider on a zebra, the model won't know how to describe it.
So, it's not just seeing the zebra, but also the context. It's seeing a situation that wasn't trained on.
Exactly. And that's a common issue. The model sees patterns, but it can't always grasp the full meaning.
It looks like it's still a research tool.
Well, right now. The results are impressive, but not yet perfect. It's a new kind of model, and it's exciting for future use cases.
What kind of future use cases do you envision?
Well, describing images for the visually impaired is one. Imagine being able to transcribe scenes from video. And it could help with other tasks that need to describe images or situations.
So, it's really a stepping stone towards more sophisticated AI?
Absolutely. The NeuralTalk 2 model is a fascinating example of how powerful deep learning can be when it comes to image description.
So, deep learning models are trained on massive datasets? That's a huge amount of data.
Yeah, absolutely. And that dataset needs to be diverse enough so it doesn't become overly biased or make faulty assumptions.
Interesting point. So, future development will focus on improving the training data, right?
Precisely. It's about getting more data to ensure the model can handle more complex scenarios, even those it hasn't encountered before. And that's where real progress lies.
Sounds promising. But are there any challenges?
Definitely. Bias in the dataset can definitely skew the results. And, as we discussed, there are still limitations in understanding context fully.
So, Torch Hub, this sounds like a powerful way to access pre-trained models. How does it work exactly?
Yeah, it's a real game changer. Imagine you want to use a pre-trained model, but it's not built into a standard library like Torch Vision. Torch Hub acts as a central repository for these models.
So, authors can upload their models to this hub?
Exactly. They put a special file called hubconf.py on GitHub. This file acts as a sort of instructions manual for loading their models.
And what's in this file?
Well, it specifies any external dependencies the model needs, like certain libraries. It also lists functions for actually initializing and loading the model.
So, it's basically a guide?
Precisely. And that's what Torch.hub uses to find and load models. Think of it like a library catalog for pre-trained models.
How do I use one of these models then?
It's super easy. You import Torch.hub, specify the GitHub repo and model name, and any additional parameters.
So you pull it directly from GitHub without even cloning it?
That's right. Torch Hub downloads a snapshot of the model, the needed files, weights, and all. It saves time and space.
What about when a dependency isn't met?
It'll tell you which packages are missing. Torch Hub won't install them automatically, but it's explicit so you know what to install.
So, it's great for access, but does it maintain quality control?
It really depends on the community. Authors choose to put their models here, and the quality varies. We can find models using Google, and check the hubconf.py file.
That's a good point. So, the flexibility is nice, but we have to do a little research.
Exactly. But having such a large and diverse collection is fantastic. It gives researchers lots of options for different tasks, not just vision.
Interesting. So, the entry points in the hubconf.py file define how to load the model, correct?
Correct. They're functions inside the file, and they're crucial for loading the model itself. They often also deal with pre-processing and post-processing steps.
This sounds powerful. What are the limitations of this approach?
Well, it's quite new, so the variety of published models is still relatively limited. The community needs to build up the repository more.
You're highlighting the growth potential of this approach, though. It's very exciting. So, Samuel, we've covered building custom models. Now, what about using pre-trained ones?
Yeah, that's a huge time saver. Imagine having a model already skilled in image recognition, and you just need it to identify different types of birds, for example.
So, you fine-tune it?
Exactly. You don't start from scratch. You leverage the existing knowledge and adjust it for your specific task. It's like taking a well-trained chef and having them cook a slightly different dish.
Makes sense. Why is this useful practically?
Well, if you're working with a dataset that's not enormous, fine-tuning a pre-trained model can be way more effective than building a brand new one from scratch.
So, a smaller dataset?
Exactly. You get much better results with less data. Plus, you're not waiting months to train from nothing.
Sounds efficient. What about PyTorch's role in this?
PyTorch provides the tools to do this easily. It's a good toolbox, not overly complicated.
So, it's not like a giant library that's overwhelming?
Exactly. That's part of its appeal. You can focus on the core components, not get bogged down in a mountain of features.
Interesting. Is there a drawback to using pre-trained models?
Potentially, yes. The pre-trained model might be very good at general tasks, but not perfect for your particular fine-tuning need. It has bias from how it was originally trained, so the results might not be as great as a custom model for that specific niche task.
So, you need to be mindful of that.
Absolutely. You need to understand its strengths and limitations. But overall, it's a powerful approach.
Okay, so pre-trained models, fine-tuning, and understanding the trade-offs. We're getting into the nitty-gritty.
Absolutely. And the next chapter, it's time to dive into tensors, the fundamental building blocks of PyTorch models.
Looking forward to it.